Welcome to the Foundry by Forge College. Today, we're diving straight into tuning our Solana application engine for a lesson titled Performance-Driven Deployment Choices. In our last explainer, we laid out the architectural blueprints, right? We learned exactly how to get your code live without, breaking the internet. But today we are tackling the terrifying question, is it actually fast, or is it just kind of pretending to be? We're taking this from the blueprints straight to measurable performance outcomes. So, let's get into it.
All right, here's our blueprint for today's explainer. We're going to cover the performance challenge, latency versus throughput, diagnosing bottlenecks, real-world workloads, benchmarking workflow, and wrap it all up with some final takeaways.
Part 1, the performance challenge, from blueprints to the test track.
Part 2, latency versus throughput, speed versus volume.
So once your code is live, you've really got to stop guessing. You need to start treating your deployment like a rigorous scientific experiment. Because in the world of Web3, you're constantly battling two completely different forces, latency and throughput. Think of latency as the top speed of a single sports car on a racetrack. It's the exact, literal time between a user clicking buy and seeing that confirmed response. Throughput, on the other hand, well, that's the width of your highway. How many minivans can we cram onto this road at the exact same time without causing a massive traffic jam? And here's the catch. You usually have to tune your deployment for one or the other. I mean, you can't really have a 100-lane highway made entirely of sports cars. Well, I guess you could, but no way you're paying for that. It gets way too expensive, way too fast.
So how do we actually measure this speed? Well, if you're relying on average latency, I have some terrible news for you. Average latency, it's basically a lie. It's a mathematical illusion perfectly designed to hide that one user who's literally screaming at their monitor because their transaction just froze. And that is exactly why engineers use percentiles like P50, P95, and P99. That P99 metric tells you the absolute worst-case scenario that 1 out of every 100 users is currently suffering through. Think about it. If your average response time is a snappy 50 milliseconds, but your P99 is sitting at 3 seconds, your system isn't actually fast. You're just getting inconsistently lucky. We absolutely must optimize for the tail end, because that is exactly where user frustration lives.
Moving on to Part 3, diagnosing bottlenecks, the diagnostic manual.
Okay, so when those P99 numbers spike out of nowhere, it's time to open up the manual. Let's map out our specific pain points directly to some concrete deployment mitigations. First up on the list, network round-trip time. Look, if your user is sitting in Tokyo and your node is over in New York, basic physics is going to totally ruin your median latency. The fix here? Deploy edge RPCs physically closer to them. Next up is RPC queuing. If you under-provision your threads, requests are just going to get stuck in line like a really bad theme park ride. You fix this one with RPC autoscaling. Then we have cold starts. This is when your serverless processes have to wake up from a deep sleep, and boom, massive latency spikes. The solution is to keep warm pools of instances ready to go, essentially with the running shoes already on. And finally, application contention. Single-threaded bottlenecks will absolutely flatline your throughput. The mitigation? Shard the work and deploy parallel workers.
Part 4, real-world workloads. Let's take this for some test drives. Let's look at 3 specific test drives. We'll start with a low-latency trading UI. In interactive trading, latency is the absolute king. We want sub-100 millisecond response times end-to-end. If price updates lag by even half a second, users lose money. And believe me, they will absolutely let you know about it on social media. So, to prevent this nightmare, we placed warmed RPC proxies at edge locations worldwide. We also specifically reduce our RPC batch sizes. You see, batching inherently creates a tiny delay while it waits around to group transactions together. But in a trading UI, we don't wait for anyone. We want that single request out the door instantly.
Now, on the flip side, let's look at a massive high-throughput Mint. This is a burst scenario. We're talking thousands of transactions hitting your backend in a matter of seconds. Here, single request latency doesn't really matter. It is all about sheer volume. To survive this kind of onslaught, we horizontally scale our minting workers to process everything in parallel. Remember how we just avoided batching for the trading UI? Well, here, we aggressively implement application-level batching. Grouping independent operations into fewer RPC calls acts as a massive force multiplier for your efficiency. We also want to strip away any unnecessary synchronous coordination. Because if your app has to stop and double-check a global order for every single NFT mint, you're going to instantly create a bottleneck and have your throughput.
Okay, but what if you have both? A mixed workload where heavy background data crunching is running right alongside a snappy, interactive API. The absolute golden rule here is workload isolation. You've got to put up a wall. Set up separate RPC pools, one dedicated strictly to the heavy lifting and one just for the UI. For the UI pool, you maintain a steady, warm baseline to guarantee that low latency. But for the background tasks, that's where you apply aggressive, cost-effective auto-scaling. By completely isolating these workloads, you keep your massive background traffic entirely out of the fast lane of your interactive user traffic.
Part 5. Benchmarking workflow. Let's look at the telemetry. As the saying goes, you can't improve what you don't measure. But setting up telemetry doesn't have to break the bank. You can actually write a super simple Node script to act as an RPC probe, just sending concurrent get version calls. And because get version is read-only, it requires absolutely no wallets, no signatures, and zero funds. It's essentially a lightweight ping that lets you safely benchmark both latency and throughput. It allows you to really test your endpoints under heavy load. That way, you can map out exactly where your latency explodes into a giant spike, long before it ever affects a real user.
So when you're tuning your deployment, you really want to follow this exact step-by-step decision workflow. Step 1. Classify your workload. Is it latency sensitive, burst-oriented, or mixed? Step 2. Define your success metrics. What is your exact target P95 latency, or your target TPS? Step 3. Instrument and benchmark. Use those simple probes we literally just talked about. Step 4. Select your mitigations. Maybe that means edge RPCs, or maybe it's warm pools. And finally, step 5, validate and iterate. Deploy this to a canary environment and see if the data actually matches your hypothesis. This workflow perfectly connects those abstract deployment patterns directly to measurable, undeniable outcomes.
And that brings us to Part 6, Final Takeaways, the sign-off.
Let's wrap up our time in the workshop today with one overarching philosophy you should definitely take home with you. Treat each deployment decision as an experiment. Don't just apply a topology because it sounds impressive on Twitter, right? Observe your metrics, actually test your network shape, run those probes, and iterate based on actual hard data. And above all else, always prioritize the user's experience by tracking that tail behavior, not just the averages.
And honestly, that sets us up perfectly for our next challenge. Now that you know exactly how to measure performance, are you ready to plan auto-scaling policies and capacity buffers? To continue this journey, I highly encourage you to head over to forge.college to explore the next lesson on scalability considerations in deployments, along with plenty of other amazing Web3 courses. This explainer was brought to you by Forge College. Keep experimenting, keep measuring, and I'll catch you in the next explainer.